Hello there, and welcome to another gentle journey with my channel. Tonight, we're going to drift through one of the universe's most elusive mysteries, floating alongside particles so ghostly they barely exist at all. These are neutrinos, the phantom messengers from distant stars, and they're streaming through you right now as you listen to my voice. Trillions upon trillions of them, passing through your body every second without so much as a whisper. Now, I should probably warn you up front. While this video is designed to help you unwind and settle into peaceful rest, there's always the small risk that the story of these cosmic ghosts might be just fascinating enough to keep you listening. But if you do find yourself wide awake at 3 in the morning, wondering about invisible particles from the sun, well, at least you'll have learned something rather extraordinary about the hidden universe around us. Before we begin our quiet exploration, I'd love to know where in the world you're watching from tonight and what time it is in your corner of the cosmos. Whether it's midnight in Manchester, dawn breaking in Delhi, or a lazy Sunday afternoon somewhere in between, you're very welcome here. If you enjoy these gentle scientific journeys, please consider giving this video a like and subscribing to the channel. It helps more fellow wanderers find their way to these peaceful explorations of science. And just a gentle reminder, while we'll touch on some physics and particle interactions tonight, this video is purely for educational and relaxation purposes. It's not intended as scientific advice or a substitute for formal study. If you're pursuing research in particle physics, please consult peer-reviewed sources and qualified professionals. So, close your eyes if you'd like, let your shoulders drop, and take a slow, deep breath. Tonight, we're going to follow the trail of the universe's most secretive travelers, particles so shy they can pass through entire planets without bumping into a single atom. We'll discover how they're born in the hearts of stars, why scientists once thought they might not exist at all, and how these ghostly messengers carry news from the most violent corners of the cosmos. Let's begin. Picture this. You're sitting quietly in your favorite chair, perhaps with a warm cup of tea, feeling perfectly still and peaceful. But the reality is quite different. At this very moment, your body is being bombarded by an invisible storm of particles. Not harmful ones, mind you, but visitors from space so numerous and so tiny that they pass right through you without your body even noticing. These are neutrinos, and they're everywhere. Right now, as you listen to my voice, roughly 100 billion neutrinos are streaming through every square centimetre of your skin every single second. They're coming from above, from below, from all sides. They're passing through the walls of your room, through the earth beneath your feet, through your pillow, your blanket, and yes, through you. Most of them began their journey in the nuclear furnace at the heart of our sun, travelling 93 million miles through the cold vacuum of space, only to slip through our planet as if it weren't even there. It's a rather humbling thought, isn't it? We think of ourselves as solid, substantial beings, but to a neutrino we're mostly empty space. In fact, to truly appreciate just how ghostly these particles are, consider this. A neutrino could travel through a wall of lead, stretching from here to the nearest star, and have only a 50-50 chance of bumping into a single atom along the way. They're the ultimate cosmic hitchhikers, travelling light and leaving barely a trace. But what exactly is a neutrino? Well, that's where our story becomes rather charming, because for many years, scientists weren't entirely sure these particles existed at all. The tale begins in the early 20th century, when physicists were just beginning to peek inside the atom and discover that the tidy, predictable world they thought they knew was actually far stranger and more mysterious than anyone had imagined. The story starts with radioactivity, that peculiar property some atoms have of spontaneously falling apart and spitting out pieces of themselves. Scientists had identified two main types of radioactive decay: alpha decay, where atoms shoot out hefty particles, and gamma decay, where they emit pure energy in the form of light. But there was also beta decay, and this one was puzzling. In beta decay, an atom would eject an electron, But when physicists carefully measured the energy and momentum before and after the process, something was missing. The books didn't balance. Energy and momentum seemed to be vanishing into thin air. This was deeply troubling for physicists, because energy conservation is one of the most fundamental laws in the universe. Energy can change from one form to another, but it can never simply disappear. It was as if you carefully counted all the coins in your pocket, then reached in and pulled out a few, only to discover that more had vanished than you'd actually removed. Where had the missing energy gone? Some scientists began to wonder if the laws of physics might be different at the atomic scale. Perhaps energy conservation was only an approximation, a rule that worked for large objects but broke down when dealing with individual atoms. It was a radical and rather unsettling possibility. But in 1930, a brilliant Swiss physicist named Wolfgang Pauli proposed a different solution, one that was equally radical but far more elegant. What if, Pauli suggested, there was another particle involved in beta decay, an invisible particle that carried away the missing energy and momentum? This phantom particle would have to be extraordinarily elusive. It would need to have virtually no mass, no electric charge, and interact so weakly with matter that it could escape from the scene of the decay without leaving any trace. Pauli called this hypothetical particle a neutrino, Italian for little neutral one. It was a beautifully simple solution to the puzzle, but it created an almost impossible challenge for experimenters. How do you detect a particle that barely interacts with matter? How do you catch a ghost? For over 20 years, the neutrino remained purely theoretical, a mathematical construct that explained the missing energy but couldn't be directly observed. The challenge was rather like trying to prove the existence of a shadow that casts no darkness, or a whisper that makes no sound. Scientists knew neutrinos should be there, streaming out from every radioactive decay, but catching one seemed nearly hopeless. If neutrinos could pass through light years of solid lead without interacting, what hope did anyone have of building a detector sensitive enough to spot them? But here's where the story becomes truly remarkable, because sometimes in science, the seemingly impossible becomes merely very, very difficult. And very, very difficult is exactly the sort of challenge that brings out the best in human ingenuity and determination. The breakthrough came from thinking about the problem differently. If individual neutrinos are nearly impossible to catch, what about building a detector in a place where neutrinos are so numerous that even their incredibly rare interactions might occasionally happen? And where might you find such a place? Well, near a nuclear reactor, where the process of splitting uranium atoms produces neutrinos by the trillions. In the 1950s, two American physicists named Clyde Cowan and Frederick Rines had exactly this idea. They realized that while the chance of any single neutrino interacting with matter is vanishingly small, if you have enough neutrinos streaming through a detector, and if you wait patiently enough, you might just catch a few of them in the act. They built their detector near a nuclear reactor at the Savannah River plant in South Carolina, a facility that was producing plutonium for nuclear weapons. The reactor was generating neutrinos at a truly staggering rate, roughly 10 to the 20th power, or 100 billion neutrinos every second. Even with odds of interaction so low that they defied common sense, Cowan and Rines calculated that their detector should catch a few neutrinos every hour. Their detector was an ingenious contraption, rather like a very sophisticated version of those carnival games where you try to catch floating ducks with a net. Only in this case, the ducks were invisible, moved at nearly the speed of light, and had virtually no desire to be caught. The detector consisted of large tanks filled with water laced with cadmium. When a neutrino very occasionally interacted with a proton in the water, it would create a brief flash of light, a tiny cosmic firework that sensitive instruments could detect. For months, Cowan and Rines sat patiently beside their detector, watching and waiting for the telltale flashes that would prove neutrinos really existed. It was rather like fishing in a lake where the fish are invisible, the line is invisible, and you're not even sure there are any fish. But slowly, carefully, they began to see the flashes. Not many, just a few per hour, exactly as their calculations had predicted. On June 14th, 1956, Cowan and Rines sent a telegram to Wolfgang Pauli, the physicist who had first proposed the neutrino's existence 26 years earlier. The telegram was brief but momentous. "We are happy to inform you that we have definitely detected neutrinos." Pauli, who had famously worried that he had proposed a particle that could never be observed, reportedly interrupted a conference to share the news and then treated everyone to champagne. It was a triumph of both theoretical insight and experimental determination. The ghost particle was real, but this was just the beginning of the neutrino story, because as scientists would soon discover, the neutrinos from nuclear reactors were only one type among many. The universe, it turned out, was filled with neutrinos from dozens of different sources, each carrying its own unique message about the cosmic processes that created them. The most abundant neutrinos in our local neighborhood come from the nuclear fusion reactions powering our sun, deep in the solar core, where temperatures reach 15 million degrees Celsius and pressures are 250 billion times greater than at Earth's surface. Hydrogen nuclei are being crushed together to form helium. This process releases tremendous amounts of energy, some of which emerges as the sunlight that warms our planet. But for every bit of sunlight the sun produces, it also creates a flood of neutrinos. These solar neutrinos are born in the very heart of our star, in reactions so fundamental they're essentially the reason our sun shines at all. When 4 hydrogen nuclei fuse to create one helium nucleus, the process releases not just energy, but also 2 neutrinos. And because the sun is fusing roughly 600 million tons of hydrogen every single second, it's producing neutrinos at a rate that staggers the imagination. Every second, the sun sends roughly 65 billion neutrinos streaming through every square centimetre of Earth's surface. They arrive here just 8 minutes and 20 seconds after being created in the solar core, having travelled at nearly the speed of light through the vacuum of space. But here's the remarkable thing. While the sunlight that left the sun's surface at the same time as these neutrinos took that same 8 minutes to reach us, the neutrinos themselves were actually created much, much earlier. You see, while neutrinos can zip through matter as if it barely existed, light has a much harder time escaping from the sun's interior. A photon of light created in the solar core will bounce around randomly inside the sun for anywhere from 10,000 to 1,000,000 years before finally reaching the surface and streaming off into space. So the sunlight, warming your face right now, began its journey sometime between the last ice age and the dawn of human civilization, while the solar neutrinos passing through your body were created just minutes ago. It's a rather poetic thought, isn't it? The light and warmth we receive from the sun carries news that's thousands of years old, while the ghostly neutrinos bring us real-time updates from the stellar furnace that powers our solar system. In a very real sense, neutrino detectors are not just scientific instruments, but cosmic news services, delivering fresh reports from the heart of our star. But the sun is far from the only source of neutrinos in our cosmic neighborhood. Every time a cosmic ray, a high-energy particle from deep space, slams into Earth's upper atmosphere, it creates a cascade of secondary particles, including neutrinos. Nuclear power plants around the world are constantly producing neutrinos as a byproduct of splitting uranium atoms. Even the natural radioactivity in the rocks beneath our feet generates a steady trickle of these ghostly particles. And then there are the neutrinos from the most violent events in the universe. When a massive star reaches the end of its life and explodes in a supernova, the blast produces more neutrinos in 10 seconds than our sun will create in its entire 10 billion year lifetime. These supernova neutrinos carry energy levels that dwarf anything produced by human technology, and they bring us news of cosmic catastrophes happening thousands of light years away. Perhaps most intriguingly of all, the universe is thought to be permeated by a background sea of neutrinos left over from the Big Bang itself. These relic neutrinos created in the first few seconds after the universe began, are still streaming through space 14 billion years later. They're incredibly difficult to detect because they carry so little energy, but they represent a kind of fossil record of the universe's earliest moments, a faint whisper from the very beginning of time and space. As you lie there listening to this gentle exploration, it's worth taking a moment to appreciate the truly extraordinary nature of what's happening around you. You are, quite literally, being touched by the stars. Neutrinos that began their existence in nuclear reactions within distant suns are passing through your body at this very moment. Messages from cosmic explosions that happened millions of years ago are streaming silently through your bedroom. The ghostly remnants of the Big Bang itself are flowing past your pillow as you drift towards sleep. It's a reminder that we are not separate from the universe, but intimately connected to it in ways both seen and unseen. The atoms in your body were forged in the nuclear furnaces of ancient stars, and now those same stellar processes continue to send their invisible messengers through your very being. You are not just in the universe is flowing through you, particle by ghostly particle, carrying news from the deepest reaches of space and time. And yet, despite being touched by this cosmic symphony every moment of our lives, we remained completely unaware of neutrinos for most of human history. It's rather like discovering that your house has been filled with invisible guests for years, politely going about their business without ever announcing themselves or asking to use the bathroom. The challenge of studying these elusive particles has led scientists to some truly extraordinary lengths. Because neutrinos interact so rarely with ordinary matter, detecting them requires building some of the most sensitive and isolated instruments ever created. And by isolated, I mean really isolated. Many neutrino detectors are buried deep underground, sometimes more than a mile beneath the Earth's surface, hidden away in abandoned mines or specially excavated caverns. Why underground, you might wonder? Well, while neutrinos can zip through a mile of solid rock without batting an eye, other particles from space are not quite so ethereal. Cosmic rays, those high-energy particles constantly bombarding our planet, create a background noise that would overwhelm any attempt to detect the subtle whispers of passing neutrinos. By burying detectors deep underground, scientists create a sanctuary where only the most ghostly particles can penetrate. Imagine, if you will, a cathedral of science carved from living rock, a place where the only visitors are invisible messengers from the stars. These underground laboratories are among the quietest places on Earth, not in terms of sound, but in terms of particle interactions. They are temples dedicated to listening for the universe's most subtle conversations. One such detector, built in a former zinc mine in Minnesota, consists of a tank containing 50,000 tons of mineral oil. That's roughly equivalent to the weight of 300 blue whales, all of it sitting perfectly still in an underground cavern, waiting patiently for the occasional neutrino to announce its presence with a tiny flash of light. Another, located deep beneath a mountain in Italy, uses 37 tons of liquid argon, cooled to minus 186 degrees Celsius, so cold that the detector must be insulated like a thermos bottle to prevent the surrounding rock from warming it up. These detectors are marvels of engineering and patience. Some experiments run for years, collecting data one ghostly interaction at a time, building up a picture of the neutrino universe with the same painstaking care that astronomers once used to map the positions of stars. The scientists who work with these instruments have elevated waiting to an art form, understanding that the most profound discoveries sometimes require not just brilliant ideas, but also the willingness to listen very, very carefully for a very, very long time. And what have we learned from all this careful listening? Well, for one thing, we've discovered that neutrinos are even more mysterious than we first thought. When scientists finally developed the technology to detect solar neutrinos in the 1960s, they found something puzzling. The detectors were catching only about 1/3 as many neutrinos as theoretical calculations predicted the sun should be producing. This became known as the solar neutrino problem, and it sparked decades of scientific soul-searching. Either our understanding of how the sun works was fundamentally flawed, or something very strange was happening to neutrinos during their 8-minute journey from the solar core to Earth. Some scientists wondered if the sun's nuclear furnace was sputtering, running at a lower temperature than expected. Others proposed more exotic explanations involving new physics or undiscovered properties of neutrinos themselves. The solution, when it finally came, was both elegant and revolutionary. It turned out that neutrinos were not the simple, unchanging particles scientists had assumed them to be. Instead, they were shapeshifters, capable of transforming from one type into another as they travelled through space. The sun was producing exactly the number of neutrinos theory predicted, but by the time they reached Earth, many had changed into different varieties that the early detectors couldn't see. This discovery revealed that neutrinos come in 3 distinct flavors, rather like cosmic ice cream. There are electron neutrinos, muon neutrinos, and tau neutrinos, each associated with a different type of particle interaction. What's more, these neutrino flavors can oscillate, changing back and forth as they travel, like a cosmic game of musical chairs played at the speed of light. This neutrino oscillation was far more than just a curious property of subatomic particles. It had profound implications for our understanding of the fundamental nature of matter and energy. The fact that neutrinos could change flavors meant they had to have mass, even if that mass was incredibly tiny. And this discovery helped solve one of the great puzzles of cosmology: why the universe contains enough matter to form stars and galaxies at all. You see, according to our best theories of the Big Bang, the early universe should have produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other in a burst of pure energy, leaving nothing behind. By this logic, the universe should be empty, filled with nothing but radiation from the mutual destruction of all particles. The fact that we exist at all suggests that something tipped the cosmic scales slightly in favor of matter over antimatter. Neutrinos, with their ability to oscillate between different types, might be part of the answer to this puzzle. Some theories suggest that in the incredibly hot, dense conditions of the early universe, neutrino oscillations could have created a tiny imbalance that favored matter over antimatter. If true, this would mean that we owe our very existence to the ghostly properties of these elusive particles. We are here because neutrinos are shapeshifters. It's a rather profound thought, isn't it? The fact that you can lie in bed tonight, listening to these words, contemplating the nature of invisible particles, might ultimately be thanks to quantum mechanical processes involving neutrinos in the first moments after the Big Bang. The universe's capacity for self-reflection, embodied in your consciousness at this very moment, could be a direct consequence of neutrino physics 14 billion years ago. But neutrinos aren't content to merely explain our cosmic origins. They also serve as messengers from some of the most dramatic events in the universe. When a massive star, many times heavier than our Sun, reaches the end of its life, it faces a crisis. The nuclear fuel that has kept the star shining for millions of years finally runs out, and without the outward pressure of radiation to support it, the star's core begins to collapse under its own immense gravity. What happens next unfolds in a matter of seconds, but the violence is almost beyond imagination. The stellar core, containing more mass than our entire Sun, collapses from the size of Earth to the size of a city in less time than it takes to blink. The matter becomes so dense that a teaspoon of it would weigh as much as a mountain. This creates a shock wave that races outward through the star, heating the stellar material to temperatures of 100 billion degrees and creating pressures that dwarf anything found in the Sun's core. In these extreme conditions, something remarkable happens. The collapsing stellar core becomes a neutrino factory of staggering proportions. In just 10 seconds, the dying star produces more neutrinos than our Sun will create in its entire 10 billion year lifetime. These neutrinos carry away 99% of the energy released in the explosion, vastly more than the visible light that creates the brilliant supernova we might see in the night sky. From our perspective on Earth, this means that neutrinos from a supernova arrive carrying news of cosmic catastrophe. They stream through space at nearly the speed of light, bringing word of stellar death from distances so vast that the light from the explosion might not reach us for hours or days. In a very real sense, neutrino detectors serve as early warning systems for some of the most violent events in the universe. This actually happened in 1987, when detectors on Earth registered a burst of neutrinos from a supernova in the Large Magellanic Cloud, a small galaxy neighbouring our own Milky Way. The neutrinos arrived about 3 hours before the light from the explosion became visible to telescopes, providing astronomers with advance notice that a star had just died in spectacular fashion, some 160,000 light-years away. It was the first time humans had detected neutrinos from beyond our solar system, a moment that opened an entirely new window on the universe. Just as Galileo's telescope revealed craters on the Moon and moons around Jupiter, neutrino astronomy promised to show us cosmic phenomena that remained invisible to ordinary light. We had learned to see with ghost particles, to observe the universe through the eyes of its most elusive messengers. And the messages they bring are extraordinary. High-energy neutrinos detected by observatories like IceCube, a detector built into the Antarctic ice sheet, have been traced back to some of the most energetic objects in the universe. Blazars, supermassive black holes that shoot jets of particles across millions of light-years of space. These cosmic lighthouses, spinning at the centers of distant galaxies, accelerate particles to energies that make our most powerful accelerators look like gentle breezes. When these ultra-high energy particles interact with matter or radiation, they can create neutrinos so energetic that a single particle carries more power than a professional baseball traveling at 60 miles per hour. These neutrinos then stream across the universe, carrying news of the black holes that created them. By the time they reach Earth, they've traveled for millions or even billions of years, but they arrive still carrying the signature of their violent birth. As you rest there in the quiet darkness, it's worth reflecting on the fact that some of the neutrinos passing through your body at this very moment began their journey in the accretion disk of a supermassive black hole when the universe was young. They've been traveling through space since before our solar system formed, crossing distances so vast that light from the same source is only just now reaching Earth for the first time. These ancient messengers are living fossils, unchanged since their creation billions of years ago. While galaxies have formed and evolved, while stars have been born and died, while life has emerged on countless worlds, these neutrinos have simply travelled, carrying their messages through the cosmic dark, waiting for the moment when they might finally interact with matter in some distant detector and tell their story. And this is where our story takes a rather remarkable turn, because scientists have discovered that neutrinos might be more than just cosmic messengers. They might actually be windows into physics beyond our current understanding, glimpses of phenomena that could reshape our entire picture of reality. You see, the standard model of particle physics, our best current theory of how the fundamental particles and forces work, has a curious blind spot when it comes to neutrinos. According to this model, neutrinos should be massless, zipping through the universe at exactly the speed of light, unchanging and eternal. But the discovery of neutrino oscillation, that remarkable ability to transform from one flavor to another, proves that neutrinos must have mass, even if that mass is almost impossibly small. How small are we talking? Well, if an electron were scaled up to the size of a marble, a neutrino would still be smaller than a grain of sand. In fact, it takes roughly 10 million neutrinos to equal the mass of a single electron, and electrons are already among the lightest particles we know. Neutrinos are so light that for decades their mass was considered to be zero simply because no experiment was sensitive enough to measure anything so tiny. But tiny doesn't mean insignificant. especially when you're dealing with particles that fill the entire universe. Remember, neutrinos are everywhere, streaming through space in numbers that boggle the mind. If each individual neutrino has even the tiniest bit of mass, then collectively, all the neutrinos in the universe might contribute significantly to the total amount of matter and energy in the cosmos. This leads us to one of the great mysteries of modern cosmology: dark matter. Astronomers have discovered that the visible matter in the universe, all the stars and planets and gas clouds we can see, accounts for only about 5% of the total mass and energy. The rest is invisible, detectable only through its gravitational effects on the matter we can see. Something is out there, something that outweighs all the visible matter in the universe by more than 5 to 1, but we don't know what it is. Could neutrinos be the answer? It's a tantalizing possibility, but the numbers don't quite work out. Even with their vast abundance, neutrinos appear to be too light to account for all the missing matter. Still, they likely contribute something to the cosmic inventory, and understanding exactly how much could help us solve one of the deepest puzzles in all of science. But neutrinos might reveal their secrets in other ways. Deep beneath the mountains of Italy, scientists are conducting an experiment that sounds like something from a fairy tale. They've filled an enormous underground tank with liquid xenon, cooled to -100 degrees Celsius, and surrounded it with instruments so sensitive they can detect the collision of a single particle with a xenon atom. The experiment is called Xenon, and its goal is breathtakingly ambitious: to catch dark matter particles in the act of interacting with ordinary matter. The theory is that dark matter particles, whatever they are, should occasionally bump into the xenon atoms, creating tiny flashes of light that the detectors can measure. It's rather like trying to catch snowflakes in a dark room using only the faintest of flashlights, except the snowflakes are invisible and might not exist at all. What does this have to do with neutrinos? Well, neutrinos represent the ultimate background noise for such an experiment. Remember, trillions of neutrinos are streaming through the detector every second, and while the vast majority pass through without interacting, occasionally one will bump into a xenon atom and create exactly the kind of signal the experiment is looking for. Scientists have to understand neutrino interactions with exquisite precision to distinguish between the whisper of a neutrino and the hoped-for signature of dark matter. In a delicious twist of scientific irony, the particles that were once considered impossible to detect have now become a source of unwanted noise in experiments, designed to find something even more elusive. Neutrinos, the ghosts of the particle world, are now haunting efforts to find particles that might be even more ghostly than they are. This interplay between known and unknown particles highlights something beautiful about the scientific process. Each discovery opens new questions. Each answer reveals new mysteries. The detection of neutrinos, once thought impossible, has now enabled experiments that push the boundaries of the impossible even further. We've learned to see ghost particles so that we might glimpse something beyond ghosts entirely. But perhaps the most profound implications of neutrino research lie not in what they might reveal about dark matter or cosmic structure, but in what they tell us about the nature of reality itself. The discovery that neutrinos oscillate between different flavors was the first clear evidence that the standard model of particle physics, successful as it has been, is incomplete. This incompleteness isn't a failure of science, but rather a sign of its vitality. Science progresses not by achieving final answers, but by discovering better questions. The fact that neutrinos surprised us, that they behaved in ways our theories didn't predict, means they've opened a door to new physics, new ways of understanding the fundamental workings of the universe. Some theories suggest that neutrinos might be their own antiparticles, unlike other particles which have distinct antimatter counterparts. If true, this could help explain why the universe contains more matter than antimatter, solving one of cosmology's deepest puzzles. Other theories propose that neutrinos might be connected to extra dimensions of space, curled up so small we can't detect them directly, but revealed through the subtle behavior of these ghostly messengers. There are even wilder possibilities. Some physicists speculate that neutrinos might be Majorana particles, named after the Italian physicist Ettore Majorana, who mysteriously disappeared in 1938. Majorana particles would be their own antiparticles, and their existence could point toward a deeper symmetry in the laws of physics, a hidden elegance that connects matter and antimatter in ways we're only beginning to understand. As you lie there in the gentle darkness, perhaps beginning to feel the pull of sleep, consider that the neutrinos streaming through your body might be carrying more than just news from distant stars. They might be messengers from realms of physics we haven't yet discovered, ambassadors from aspects of reality that exist beyond our current comprehension. This is the remarkable thing about neutrinos. They remind us that the universe is far stranger and more wonderful than we ever imagined. These particles that barely interact with anything, that can pass through entire planets without leaving a trace, have revealed oscillations and mass where we expected none. They've shown us that even the most ghostly aspects of reality can have profound consequences for the structure and evolution of the cosmos. And they've taught us humility. For most of human history, we were completely unaware that trillions of these particles were streaming through us every second. We lived our lives, loved and lost, built civilizations and composed symphonies, all while being constantly bathed in an invisible sea of cosmic messengers. It makes you wonder what else might be flowing around us, unnoticed and undetected, waiting for future generations to develop the tools and insights needed to reveal their presence. The story of neutrino research is also a testament to human persistence and ingenuity. From Pauli's theoretical insight in 1930 to the massive underground detectors of today, scientists have spent nearly a century learning to see the unseeable, to catch particles that seem designed by nature to be uncatchable. They've moved mountains, literally in some cases, building laboratories miles underground. They've cooled liquids to temperatures that barely exist in nature and built instruments sensitive enough to detect the collision of invisible particles. All of this effort has been driven by curiosity, by the deeply human desire to understand our place in the cosmos. Neutrino research doesn't promise immediate practical applications or technological breakthroughs. It won't cure diseases or solve energy crises. What it offers instead is something perhaps more precious: knowledge, understanding, a clearer picture of the universe we inhabit and our connection to it. The neutrinos passing through you as you listen to these words carry stories from the heart of the sun, from the death throes of distant stars, from the first moments after the Big Bang. They connect you to processes happening millions of light years away and events that occurred billions of years ago. In a very real sense, you are part of a cosmic conversation, a dialogue between matter and energy that spans space and time. This conversation is ongoing, unfolding every moment in detectors buried deep beneath mountains and ice sheets around the world. Right now, as you settle deeper into rest, scientists are monitoring instruments that might catch the next burst of neutrinos from a distant supernova, or detect the subtle signature of neutrino oscillation, or perhaps glimpse something entirely unexpected that will reshape our understanding of reality once again. The beautiful thing about this research is that it requires patience, the kind of deep, contemplative patience that seems increasingly rare in our fast-paced world. Neutrino experiments unfold over years and decades. They require scientists to sit quietly, to listen carefully, to wait for the universe to whisper its secrets. There's something almost meditative about it, this practice of sustained attention to the barely detectable. In many ways, neutrino research embodies the same qualities that make for peaceful sleep: stillness, patience, receptivity to subtle signals, the willingness to let go of expectations and simply observe what unfolds. Perhaps that's why the story of these ghost particles makes such perfect bedtime listening. Like sleep itself, neutrinos operate in a realm beyond our ordinary consciousness, carrying out their cosmic business while we rest. unaware but somehow participating in something vast and meaningful. The neutrino detectors scattered around the world are like meditation bells, marking the passage of particles through space and time, recording the slow rhythm of cosmic events. They remind us that the universe operates on timescales far longer than human lifespans, and that some truths can only be revealed through patient observation and careful listening. As you drift towards sleep tonight, you might imagine yourself as a kind of neutrino detector, quietly receptive to the subtle influences that flow through your life. Just as neutrinos carry information across vast distances with barely a whisper, perhaps your dreams tonight will carry messages from the deeper parts of your psyche, soft signals that emerge only when you're still enough to notice them. The ghost particles will continue their eternal journey, streaming through your sleeping form, connecting you to stars you'll never see and events you'll never witness directly. But in some small way, by understanding their story, by appreciating their role in the cosmic dance, you've become part of that larger narrative. You've joined the conversation between mind and cosmos, between the seen and unseen, between the immediate world of your bedroom and the infinite expanse of space and time. And perhaps that's the most profound gift that neutrinos offer us. Not just scientific knowledge, but a sense of connection to something immeasurably larger than ourselves. They remind us that we are not isolated beings on a lonely planet, but participants in a universe teeming with invisible activity, a cosmos where even the most elusive particles play essential roles in the grand story of existence. So tonight, as neutrinos from ancient supernovas slip silently through your pillow, as messengers from the solar furnace dance invisibly around your dreams, rest, knowing that you are part of something magnificent and mysterious. The universe is not empty space punctuated by lonely islands of matter, but a richly woven tapestry where even the most ghostly threads play vital roles in the cosmic design. The story of neutrinos is far from over. In laboratories around the world, scientists are preparing the next generation of detectors, instruments so sensitive they will make today's ghost catchers look primitive by comparison. Deep beneath the ice of Antarctica, researchers are expanding the ice cube detector, creating a neutrino telescope the size of a cubic kilometre. Imagine that, a scientific instrument carved from Antarctic ice, larger than most cities, designed to catch particles that barely exist. In Japan, scientists are building detectors filled with ultra-pure water, so clean that it's more transparent than air. These cathedral-sized chambers, buried beneath mountains, will wait patiently for neutrinos to create tiny rings of light, cosmic ripples that reveal the direction and energy of particles born in distant galaxies. It's rather like building enormous swimming pools for invisible fish, hoping to catch the faintest splash when they occasionally break the surface. But perhaps the most ambitious neutrino experiment of all is one that spans continents. Scientists are planning to shoot a beam of neutrinos from a particle accelerator in the United States all the way through the Earth to a detector in South Dakota, over 800 miles away. The neutrinos will travel through the planet's core as if it were empty space, arriving at their destination having changed flavor during their underground journey. It's the ultimate test of neutrino oscillation, a cosmic game of telephone played through the heart of our world. These future experiments promise to answer questions we're only beginning to ask. Will neutrinos help us understand why the universe is made of matter rather than antimatter? Can they reveal the existence of extra dimensions curled up beyond our perception? Might they carry messages from cosmic strings, those hypothetical defects in space-time left over from the universe's earliest moments? The beauty of neutrino research is that each answer spawns new mysteries. Every breakthrough in our understanding of these ghost particles opens doors to rooms we didn't even know existed. It's rather like exploring an infinite mansion where each discovered chamber reveals staircases leading to floors we never imagined. Consider, for instance, the possibility that neutrinos might not be the only nearly invisible particles in the universe. Some theories predict the existence of sterile neutrinos, particles even more ghostly than ordinary neutrinos, interacting so weakly with matter that they make regular neutrinos look positively sociable. These hypothetical particles could help explain dark matter, or they might reveal entirely new sectors of physics, shadow worlds of particles that exist alongside our own but barely touch it. Then there are the cosmological implications. The cosmic neutrino background, that sea of ancient particles left over from the Big Bang, represents one of the oldest observable phenomena in the universe. These relic neutrinos have been streaming through space for nearly 14 billion years, cooling and diluting as the universe expanded, but never disappearing entirely. They carry information about the cosmos when it was less than a second old, a time when the entire observable universe was smaller than a grapefruit and hotter than the center of the most massive stars. Detecting these primordial neutrinos would be like finding fossilized echoes of creation itself. The challenge is staggering. These ancient particles carry so little energy that they barely qualify as moving. They drift through space at speeds that would make a leisurely stroll seem frantic by comparison. Catching one would be like trying to net a feather floating on a still pond while wearing boxing gloves and a blindfold. Yet scientists are designing experiments to do exactly that, pushing the boundaries of detection technology to glimpse the universe's earliest moments. The implications extend beyond physics into philosophy and our understanding of existence itself. Neutrinos challenge our intuitions about what it means for something to be real. They have mass, but barely. They interact with matter, but almost never. They carry energy and momentum, yet slip through planets as if they were made of morning mist. In what sense do they exist? What does it mean to be substantial when you're more insubstantial than a shadow? These questions echo ancient philosophical puzzles about the nature of being and nothingness, but now they're grounded in experimental reality. We can catch neutrinos, count them, measure their properties, and use them to probe the cosmos. Yet they remain fundamentally mysterious, particles that seem to exist in the liminal space between something and nothing, between presence and absence. Perhaps this is why neutrinos make such perfect companions for the twilight moments before sleep. Like dreams themselves, they operate in a realm that's neither fully real nor entirely imaginary. They're measurable yet intangible, everywhere yet nowhere, carrying messages from distant realms while barely registering their passage through our world. As you lie there in the gentle darkness, you might imagine the neutrino streams as cosmic lullabies, sung by distant stars and carried across the universe at nearly the speed of light. Each particle is a note in an endless symphony, a composition that began with the Big Bang and continues to this day. The melody is too subtle for our ears, too gentle for our instruments to easily detect, but it's there nonetheless, a background music of the spheres that plays continuously through space and time. The scientists who dedicate their lives to studying these ghost particles are, in a sense, cosmic composers, learning to hear melodies that existed long before human ears evolved to listen. They sit in underground cathedrals of science, surrounded by instruments sensitive enough to detect whispers from the edge of existence, waiting patiently for the universe to share its most subtle secrets. Their work requires a particular kind of faith, not religious faith, but the scientific faith, that nature's deepest truths reveal themselves to those patient enough to listen carefully. It's the faith that behind the apparent chaos of quantum mechanics and the vastness of cosmic distances, there are patterns and connections waiting to be discovered. It's the belief that the universe, for all its complexity and strangeness, is ultimately comprehensible to minds curious enough to ask the right questions and persistent enough to seek the answers. This faith has been rewarded time and again in the history of neutrino research. From Pauli's desperate hypothesis, to save energy conservation, to the first detection in underground laboratories, to the discovery of oscillation and mass, each breakthrough has revealed new layers of cosmic complexity and beauty. The ghost particles that once seemed like mathematical abstractions have become windows into the universe's most fundamental processes. And the journey is far from over. The next decade promises discoveries that could reshape our understanding of reality itself. New detectors will peer deeper into space and time, catching neutrinos from the edge of the observable universe, from the first generation of stars, from cosmic events so distant their light has not yet reached us. We may finally detect those elusive sterile neutrinos, or discover that neutrinos are their own antiparticles, or find evidence that they carry information about extra dimensions folded into the fabric of space-time. Each possibility opens new questions, new avenues of exploration, new ways of seeing the cosmos. The ghost particles that once seemed like the end of the story have become the beginning of entirely new chapters in our understanding of existence. But perhaps the most profound lesson neutrinos teach us is about humility and wonder. They remind us that the universe is far richer and stranger than our everyday experience suggests. They show us that reality operates on scales both vast and tiny, from cosmic distances to subatomic interactions, all connected by invisible threads of cause and effect. Every neutrino passing through your body, as you listen to these words, is a reminder that you are not separate from the cosmos, but intimately woven into its fabric. The same processes that power distant stars and drive cosmic evolution are playing out at the quantum level within your cells. The neutrinos streaming through you connect you to supernovas that exploded before the Earth formed, to the nuclear furnace of our Sun, to the primordial fires of creation itself. This connection is not metaphorical but literal. The atoms in your body were forged in stellar cores through the same nuclear processes that create neutrinos. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of these elements were created in the hearts of massive stars and dispersed through space when those stars died in spectacular supernovas, events that flooded the cosmos with neutrinos, carrying news of stellar death and elemental birth. In a very real sense, you are made of star stuff, and neutrinos are the messengers that have been carrying news of your stellar origins across the universe for billions of years. They are the invisible threads that connect your existence to the cosmic processes that made life possible, the ghostly witnesses to the long chain of events that led from the Big Bang to this quiet moment of contemplation before sleep. As you drift toward rest tonight, carried along by the gentle rhythm of breathing and the soft cadence of these words, you might imagine yourself floating in that vast sea of cosmic neutrinos, supported by invisible currents that have flowed through space since the universe began. You are not falling asleep alone, but accompanied by trillions of ghostly companions, messengers from the stars that sing you silent lullabies in a language older than worlds. The neutrino streams will continue their eternal journey while you sleep, carrying their messages across the cosmos, connecting distant galaxies and distant times in an endless dance of matter and energy. And when you wake, refreshed and renewed, they will still be there, still flowing, still carrying news from the heart of creation to anyone patient enough to listen. In the grand symphony of existence, neutrinos are the quiet notes, the gentle harmonies that bind the cosmic melody together. They remind us that the universe speaks in whispers as well as roars, in subtle influences as well as dramatic events. They teach us that the most profound truths often reveal themselves not to those who grasp and grab, but to those who wait quietly and listen carefully for the soft voices of the cosmos. Tonight, as we continue our gentle journey through the realm of ghost particles, let's drift deeper into one of the most extraordinary chapters in the neutrino story. It's a tale that begins with a mystery so profound it made scientists question the very nature of the sun itself, and ends with a discovery that opened entirely new windows onto the cosmos. Picture, if you will, the late 1962nd. Scientists had finally developed the technology to catch solar neutrinos, those ghostly messengers streaming from the heart of our star. Deep in the Homestake gold mine in South Dakota, nearly a mile beneath the Earth's surface, sat one of the most unusual scientific instruments ever conceived, a tank containing 100,000 gallons of dry cleaning fluid. This wasn't a cosmic laundromat, mind you, but rather humanity's first serious attempt to eavesdrop on the nuclear conversations happening inside the sun. The cleaning fluid, perchloroethylene, was chosen because it contains chlorine atoms that occasionally, very occasionally, would capture a solar neutrino and transform into radioactive argon. Once every few days, scientists would flush the tank with helium gas, hoping to collect a few dozen atoms of this radioactive argon from among the countless trillions of molecules in the tank. It was rather like searching for specific grains of sand on all the beaches of the world, if those grains of sand were invisible and kept changing into different types of sand while you weren't looking. The experiment required patience on a cosmic scale and precision that would make a Swiss watchmaker weep with envy. The scientist leading this extraordinary endeavour was Ray Davis, a soft-spoken chemist who had dedicated his career to catching particles that barely existed. For months, then years, Davis and his team would descend into the mine, collect their precious few atoms of argon, and count them with instruments so sensitive they could detect radioactive decay from individual atoms. It was detective work at the most fundamental level, listening for the whispered confessions of particles born in stellar fire. But something was wrong. The numbers didn't add up. Davis was detecting solar neutrinos, which was cause for celebration, but he was finding only about 1/3 as many as theory predicted the sun should be producing. Either the sun was running cooler than anyone thought, or something very strange was happening to neutrinos during their 8-minute journey from solar core to Earth. This became known as the solar neutrino problem, and it haunted astrophysics for decades. Some scientists suggested that the sun's nuclear furnace was sputtering, perhaps cycling through periods of high and low activity like a cosmic heartbeat with an irregular rhythm. Others proposed that our understanding of stellar physics was fundamentally flawed, that the nuclear processes powering stars didn't work quite the way we thought they did. But there was another possibility, one that seemed almost too exotic to consider seriously. Perhaps the neutrinos themselves were changing during their journey through space. Perhaps these ghostly particles weren't the stable, unchanging messengers scientists had assumed them to be, but shapeshifters capable of transformation on a cosmic scale. The idea seemed outlandish at first. How could a particle change its fundamental nature while travelling through empty space? It would be like sending a letter that transformed into a telegram, somewhere between the post office and your mailbox, carrying the same message but in an entirely different form. Yet as the decades passed and the solar neutrino deficit persisted, this strange possibility began to look more and more plausible. The breakthrough came from an unexpected direction, a zinc mine in Japan, where scientists had built a detector called Kamiokande, later expanded into the magnificently named Super-Kamiokande. This wasn't a tank of cleaning fluid, but a cathedral of pure water, 50,000 tons of it, surrounded by thousands of light-sensitive detectors called photomultiplier tubes. These instruments could amplify the faintest flash of light until it became a measurable signal, like cosmic hearing aids for photons. When a neutrino occasionally interacted with the water, it would create a brief pulse of light, a tiny blue glow that lasted mere billionths of a second. The pattern of this light could reveal not just that a neutrino had arrived, but what direction it came from and how much energy it carried. For the first time, scientists weren't just counting neutrinos, they were taking their portraits. What Super-Kamiokande revealed was extraordinary. The detector could see neutrinos coming from the sun, just as expected, but it could also detect neutrinos created in Earth's atmosphere when cosmic rays slammed into air molecules. These atmospheric neutrinos were created in showers of particles high above our heads, and they came in two distinct flavors. Some were electron neutrinos, while others were muon neutrinos, each associated with different types of particle interactions. The atmospheric neutrinos provided a perfect natural laboratory for studying neutrino behavior. The detector could compare neutrinos that had traveled just a few miles through the atmosphere with others that had journeyed all the way through the Earth from the other side of the planet. If neutrinos were stable, unchanging particles, the ratios between different flavors should be the same regardless of how far they had traveled. But they weren't. The neutrinos that had traveled longer distances showed a different flavor mix than those that had made shorter journeys. It was as if the particles were playing an elaborate game of musical chairs while traveling through space, switching identities according to some hidden quantum choreography. This was the smoking gun that scientists had been seeking for decades, direct evidence that neutrinos could oscillate between different flavors. The solar neutrino problem wasn't caused by a faltering sun or flawed stellar models, but by the shape-shifting nature of the neutrinos themselves. The sun was producing exactly the number of neutrinos theory predicted, but by the time they reached Earth, many had transformed into flavors that early detectors couldn't see. It was a bit like tuning into a radio station and discovering that the music kept changing genres during the broadcast, not because the DJ was switching records, but because the radio waves themselves were transforming as they traveled through space. The message was the same, but its form had evolved during the journey. The discovery of neutrino oscillation was more than just a solution to a decades-old puzzle. It was a revelation that opened entirely new chapters in our understanding of particle physics and cosmology. For neutrinos to oscillate between different flavors, they had to have mass, even if that mass was incredibly tiny. This was the first clear evidence that the standard model of particle physics, successful as it had been, was incomplete. But the implications went far beyond particle physics textbooks. The fact that neutrinos have mass, however small, means they contribute to the total matter content of the universe. Given their vast abundance, streaming through space in numbers that stagger the imagination, even their tiny individual masses might add up to something cosmologically significant. Consider the arithmetic for a moment. There are roughly 330 million neutrinos in every cubic meter of space throughout the universe. That's more neutrinos in a volume the size of your bedroom than there are stars in the observable cosmos. If each of these particles has even the tiniest bit of mass, the collective weight of all neutrinos in the universe becomes substantial indeed. Current estimates suggest that neutrinos might account for roughly 1% of all the matter and energy in the cosmos. That may not sound like much, but it's comparable to the mass of all the stars in all the galaxies we can see. In essence, the ghostly neutrino background represents a hidden component of cosmic matter that we've only recently learned to appreciate. This neutrino contribution to cosmic mass has profound implications for how structures formed in the early universe. In the first few 100,000 years after the Big Bang, before the first stars ignited, matter was distributed almost uniformly throughout space. But tiny fluctuations in density, quantum ripples left over from the universe's earliest moments, provided the seeds around which galaxies and galaxy clusters would eventually grow. Neutrinos, with their ability to stream freely through matter in the early universe, would have smoothed out some of these primordial density fluctuations, erasing the smallest ripples while leaving larger ones intact. The result is that neutrino mass helps determine the pattern of cosmic structure we see today, the delicate web of filaments and voids that stretches across billions of light years. It's rather poetic, isn't it? The most elusive particles in the universe, barely interacting with anything, have nonetheless left their fingerprints on the largest structures in the cosmos. The same neutrinos that slip silently through your body as you lie in bed tonight helped shape the architecture of space itself, influencing where galaxies formed and how they clustered together across cosmic time. But the story of neutrino oscillation revealed something even more profound about the nature of quantum reality. The ability of neutrinos to exist in multiple flavors simultaneously, transforming from one type to another as they travel, is a manifestation of one of quantum mechanics' most mysterious features: superposition. In the quantum world, particles don't always have definite properties. Instead, They can exist in multiple states at once, like a coin that's spinning in the air, neither heads nor tails until it lands, and we observe the result. A neutrino created in the Sun's core doesn't begin its journey as a pure electron neutrino. Rather, it exists in a quantum superposition of all three neutrino flavors, with the probability of being detected as any particular type, changing as it travels through space. This quantum superposition isn't just a theoretical curiosity. It's a measurable phenomenon that affects how neutrinos behave in the real world. The oscillation between neutrino flavors is essentially a quantum wave phenomenon, with the probability of finding a particular flavor oscillating like a sine wave as the neutrino travels. The wavelength of this oscillation depends on the differences in mass between the three neutrino types and the energy of the neutrino itself. It's as if each neutrino carries within itself a tiny quantum clock, ticking away at a frequency determined by the particle's mass and energy. As the neutrino travels, this quantum clock causes the particle's identity to cycle between different flavors, like a cosmic metronome keeping time with the rhythm of space itself. This quantum mechanical behavior of neutrinos has opened new avenues for probing the fundamental nature of reality. Scientists can now use neutrino oscillation as a precision tool for measuring tiny mass differences between particles. Differences so small they make the mass of an electron seem gargantuan by comparison. These measurements provide windows into the deep structure of the quantum world, revealing patterns and symmetries that might otherwise remain hidden. The technology required to make such precise measurements pushes the boundaries of human ingenuity. Modern neutrino detectors are marvels of engineering and patience, capable of distinguishing between different types of neutrino interactions with extraordinary precision. They must be shielded not just from cosmic rays, but from the natural radioactivity in the surrounding rock, from radon gas seeping from the Earth, even from the cosmic ray muons created when particles from space interact with the atmosphere far overhead. Some detectors are so sensitive that they must account for the gravitational effects of the Moon and Sun, which cause tiny deformations in the Earth that could affect their measurements. Others must be isolated from human activity, the vibrations from traffic on distant highways, the operation of machinery miles away. Even the footsteps of researchers in neighboring laboratories can introduce unwanted noise into these delicate instruments. The scientists who work with these detectors have developed an almost monastic relationship with their instruments, understanding that the most profound discoveries often require not just brilliant insights, but also the patience to wait years for enough data to accumulate. They've learned to think in terms of statistical significance, building up their understanding of neutrino behavior one interaction at a time, like archaeologists reconstructing ancient civilizations from pottery shards and tool fragments. This patient approach to discovery reflects something deeper about the nature of neutrino research. Unlike other branches of physics where dramatic events can be staged and restaged at will, neutrino physics unfolds at its own pace, governed by the quantum probabilities that determine when these ghostly particles will finally interact with matter. Scientists can't hurry neutrinos or command them to appear. They can only create the conditions for detection and then wait, with infinite patience, for the universe to reveal its secrets. There's something deeply contemplative about this approach to science, something that resonates with the same qualities that make for peaceful sleep: stillness, receptivity, the willingness to let go of urgency and simply be present with whatever emerges. In a world increasingly dominated by the demand for immediate results and instant gratification, neutrino research represents a different way of engaging with reality, one that honors the subtle rhythms of the quantum world. As you rest there in the quiet darkness, perhaps you can imagine yourself adopting some of this same contemplative patience. Just as neutrino detectors sit quietly underground, waiting for ghostly particles to announce their presence, you too can rest in stillness, open to whatever dreams or insights might emerge from the depths of your subconscious. The same quantum processes that govern neutrino oscillation are at work in the neural networks of your brain, creating the mysterious phenomenon we call consciousness through patterns of activity too complex for any current theory to fully explain. The connection between quantum mechanics and consciousness remains one of science's great mysteries, but neutrinos offer us a tangible reminder that the quantum world isn't separate from our everyday experience. These particles demonstrate that quantum superposition and wave-particle duality aren't just abstract concepts confined to physics textbooks, but real phenomena that play out on cosmic scales, affecting the behavior of particles that travel from the hearts of stars to pass through your sleeping form. In recent years, scientists have begun to explore even more exotic possibilities for neutrino behavior. Some theories suggest that these particles might violate certain symmetries that physicists once thought were fundamental to the structure of reality. If neutrinos behave differently from their antimatter counterparts, this could help explain one of cosmology's deepest puzzles: why the universe contains matter at all. According to our best theories of the Big Bang, the early universe should have produced equal amounts of matter and antimatter. When these two forms of matter meet, they annihilate each other in bursts of pure energy, leaving nothing behind. The fact that we exist at all suggests that something tipped the cosmic scales slightly in favor of matter over antimatter, creating the tiny imbalance that eventually led to stars, planets, and life. Neutrinos, with their ability to oscillate between different flavors and their possible violations of matter-antimatter symmetry, might hold the key to this puzzle. In the incredibly hot, dense conditions of the early universe, neutrino oscillations could have created a subtle preference for matter over antimatter, a quantum mechanical bias that accumulated over time until it produced the matter-dominated cosmos we observe today. If this theory is correct, then the ghost particles streaming through your body tonight are more than just cosmic messengers. They're the reason you exist at all. The same quantum oscillations that allow neutrinos to change flavors might have tipped the balance of creation itself, ensuring that the universe would eventually become a place where matter could condense into stars and planets, where complex chemistry could unfold, where consciousness could emerge to contemplate its own origins. It's a breathtaking possibility, one that connects the most abstract realms of particle physics to the most fundamental questions of existence. The fact that you can lie in bed tonight, thinking about invisible particles from space, might ultimately be thanks to quantum mechanical processes involving neutrinos in the first seconds after the Big Bang. The universe's capacity for self-reflection, embodied in your consciousness at this very moment, could be a direct consequence of neutrino physics 14 billion years ago. This connection between the cosmic and the personal, between the vastly ancient and the immediately present, is perhaps the most profound gift that neutrino science offers us. These particles don't just carry information about distant stars and cosmic events. They carry the story of how the universe became capable of understanding itself, how matter organized itself into patterns complex enough to contemplate their own existence. As you drift deeper into the gentle embrace of approaching sleep, you might reflect on this extraordinary fact. The same processes that created the neutrinos streaming through your body also created the atoms that make up your brain, the neurons that generate your thoughts, the consciousness that allows you to appreciate the beauty and mystery of the cosmos. You are not separate from the universe, but intimately woven into its fabric, a temporary pattern of matter and energy that has organized itself into awareness, into wonder, into the capacity for peaceful rest. The neutrinos will continue their eternal journey while you sleep, carrying their messages across the cosmos, connecting distant galaxies and distant times in an endless dance of quantum transformation. They remind us that the universe operates according to principles both elegant and mysterious, that reality unfolds through processes more subtle and beautiful than our everyday experience might suggest. In the morning, when you wake refreshed and renewed, the same ghostly particles will still be streaming through you, still carrying news from the heart of the sun, still oscillating between their different quantum identities as they traverse the emptiness of space. They'll still be there, invisible and patient, waiting for the next generation of detectors to reveal new secrets about their behavior, new clues about the fundamental nature of reality itself. Until then, they flow on through the cosmic night, these messengers from the stars, these quantum ghosts that barely exist, yet somehow hold keys to the deepest mysteries of existence. They whisper their secrets to those patient enough to listen, to those willing to sit quietly in underground cathedrals of science, waiting for the faintest signals from the edge of the known universe. And in their own ghostly way, they sing you to sleep tonight, these neutrinos from distant suns, these quantum lullabies streaming at the speed of light across the infinite expanse of space and time. And here's where the neutrino story takes perhaps its most remarkable turn, because scientists have discovered that these ghost particles might be keys to unlocking one of the universe's greatest mysteries, the nature of time itself. Deep beneath the mountains of Italy, in laboratories carved from ancient stone, researchers are conducting experiments that sound like something from the realm of science fiction, yet they're grounded in the most precise measurements human ingenuity can devise. The question they're asking is deceptively simple. Do neutrinos experience time the same way we do? It's a query that strikes at the very heart of Einstein's theories of relativity, which tell us that time isn't the fixed, universal constant we perceive it to be, but rather a flexible dimension that can stretch and compress depending on speed and gravity. For most particles, these relativistic effects are predictable and well understood. But neutrinos, with their almost massless nature and their ability to travel at very nearly the speed of light, exist in a realm where the normal rules of space and time become beautifully blurred. Imagine, for a moment, riding alongside a neutrino as it streams from the core of a distant star toward Earth. From your perspective, traveling at 99.99% of light speed, the journey that takes thousands of years from our earthbound viewpoint would pass in what feels like mere moments. The universe would appear contracted in the direction of travel, distances shrinking to almost nothing, while time itself would slow to a near standstill. You would experience what physicists call time dilation, in its most extreme form, a phenomenon so profound that it challenges our most basic intuitions about the nature of reality. This isn't merely theoretical speculation. Scientists have measured these effects with extraordinary precision, timing neutrino pulses as they travel between laboratories separated by hundreds of miles. The results have yielded some of the most accurate measurements of the speed of light ever achieved, confirming Einstein's predictions with breathtaking exactness. But they've also revealed subtle anomalies, tiny deviations from expectation that hint at deeper mysteries lurking within the quantum realm. Some of these experiments have produced results so startling that they initially sent shockwaves through the physics community. In 2011, researchers at the Opera experiment in Italy announced that they had measured neutrinos arriving slightly ahead of schedule, apparently travelling faster than light itself. If confirmed, such a finding would have overturned a century of physics, suggesting that causality itself might be violated at the quantum level. The scientific response was swift and thorough. Teams around the world rushed to verify the measurements, checking and double-checking every component of the experimental apparatus. Was it a systematic error in the timing systems? A miscalibration of the GPS satellites used to synchronize clocks across the continent? A subtle effect of the Earth's rotation that hadn't been properly accounted for? The scrutiny was intense, as befits any claim that challenges the fundamental structure of physics. Eventually, the mystery was solved. A loose fiber optic cable, a connection that had gradually degraded over months of operation, had introduced a tiny timing error that made the neutrinos appear to arrive earlier than they actually had. When the cable was repaired and the measurements repeated, the neutrinos once again obeyed Einstein's speed limit, arriving precisely when relativity predicted they should. Far from being a failure, this episode demonstrated the self-correcting nature of science at its finest. The initial excitement, the careful scrutiny, the eventual resolution of the puzzle, all illustrated how scientific knowledge advances through a process of bold hypotheses followed by rigorous testing. The neutrinos had once again taught us something profound, not about faster than light travel in this case, but about the importance of meticulous experimental technique and the willingness to question even our most cherished theories when the evidence seems to demand it. But the quest to understand neutrinos' relationship with time continues in other, more subtle ways. These particles offer us a unique window into the quantum mechanical nature of time itself, because their oscillation between different flavors occurs according to a quantum clock that ticks at frequencies determined by the fundamental constants of nature. By studying how this quantum timekeeper behaves under different conditions, scientists are probing the deepest levels of temporal reality. Consider the extraordinary precision required for such measurements. To detect the subtle oscillations of neutrino flavor over cosmic distances, researchers must account for every possible source of timing error, from the movement of continental plates to the gravitational effects of distant planets. Their instruments are synchronized using atomic clocks so precise that they would gain or lose less than a second over the entire age of the universe. They measure distances using laser interferometry accurate to fractions of the width of a proton. This technological tour de force serves a purpose far grander than merely catching ghost particles. It's creating a new kind of astronomy, one that uses neutrinos as cosmic messengers to probe phenomena that remain invisible to ordinary light. Unlike photons, which can be absorbed or scattered by dust and gas during their journey through space, neutrinos travel in perfectly straight lines from their source to our detectors, carrying pristine information about the most violent and exotic processes in the universe. Through neutrino astronomy, we've begun to map the cosmos in entirely new ways. We can peer into the cores of distant galaxies where supermassive black holes devour matter at rates that boggle the imagination, heating infalling material to temperatures that exceed those found in stellar interiors. We can observe the aftermath of neutron star collisions, cataclysmic events that forge heavy elements and send gravitational waves rippling across space-time. We can even glimpse the remnants of supernovae so distant that their light has been traveling toward us since before the Earth formed. Each neutrino detection adds another point of light to this invisible map of the universe, revealing structures and processes that would otherwise remain forever hidden from our view. It's rather like developing a photograph in a cosmic darkroom, watching as faint images gradually emerge from what initially appears to be empty space. The picture that's taking shape is one of a universe far more dynamic and interconnected than we ever imagined, where events separated by billions of light years are linked by streams of ghostly particles carrying news across the cosmos. But perhaps the most profound insights from neutrino research come not from what these particles tell us about distant objects, but from what they reveal about the nature of existence itself. The fact that neutrinos can maintain their quantum coherence across cosmic distances, oscillating between different flavors while traveling for millions of years through space, suggests that quantum mechanics operates on scales vastly larger than anyone previously thought possible. This has implications that extend far beyond particle physics. If quantum effects can persist across astronomical distances, what does this tell us about the nature of consciousness, which many scientists believe emerges from quantum processes in the brain? Could it be that awareness itself is somehow connected to the same quantum fields that allow neutrinos to exist in multiple states simultaneously? The questions are speculative, even mystical, but they arise naturally from our growing understanding of how quantum mechanics operates in the real world. As you rest there in the peaceful darkness, these are the kinds of thoughts that neutrinos inspire, thoughts that bridge the gap between the rigorously scientific and the deeply philosophical. They remind us that the universe is not just a collection of objects moving through empty space, but a unified field of quantum possibilities where consciousness and cosmos are intimately intertwined. The research continues at an ever-accelerating pace. New detectors are being planned that will dwarf today's instruments in size and sensitivity. Deep beneath the ice of Antarctica, scientists are expanding the Ice Cube Observatory into a detector volume larger than many cities, capable of catching neutrinos from the edge of the observable universe. In underground laboratories around the world, teams are preparing experiments that will probe neutrino properties with unprecedented precision, perhaps finally answering the question of whether these particles are their own antiparticles. There are even more ambitious projects on the drawing boards. Some scientists envision neutrino telescopes in space, free from the interference of Earth's atmosphere and magnetic field. Others propose using the entire Earth as a detector, measuring how neutrinos are absorbed as they pass through our planet, and using this information to map the density variations deep within the Earth's core. The possibilities seem as limitless as the neutrino streams themselves. Yet, for all the technological sophistication of modern neutrino research, there remains something fundamentally contemplative about the field. Unlike other branches of physics where experiments can be repeated at will, neutrino detection requires patience on a cosmic scale. Researchers must learn to think in terms of statistical accumulation, building their understanding one interaction at a time over months and years of careful observation. This slow, meditative approach to discovery has created a unique culture within the neutrino physics community. Scientists speak of their detectors almost as living things, with personalities and moods that must be carefully tended. They develop an intimate familiarity with their instruments' every quirk and characteristic, learning to distinguish between the subtle signatures of different types of neutrino interactions with the same sensitivity that a musician brings to their instrument. There's something beautiful about this relationship between researcher and detector, this partnership between human intuition and technological precision in the pursuit of cosmic truth. It reflects a deeper harmony between the observer and the observed, a recognition that the act of measurement is itself a kind of participation in the quantum dance of reality. The neutrino detectors scattered around the world have become modern temples of scientific contemplation, places where researchers gather to commune with the deepest mysteries of existence. In these underground sanctuaries, surrounded by tons of ultra-pure materials shielded from the chaos of the surface world, scientists practice a form of technological meditation, listening for whispers from the edge of space and time. The data they collect doesn't just advance our understanding of particle physics. It feeds into models of cosmic evolution that help us comprehend how the universe developed from its earliest moments to its present complex state. Neutrino observations inform theories of stellar nucleosynthesis, the processes by which heavy elements are forged in stellar cores and dispersed through space by supernovae explosions. They provide crucial tests of our understanding of the Big Bang itself, offering windows into physical conditions that existed when the universe was less than a second old. In this way, neutrino research serves as a bridge between the infinitesimally small and the cosmically vast, between quantum mechanics and general relativity, between the laboratory and the cosmos. These ghost particles, which barely interact with anything, have become some of our most important messengers from realms of physics that would otherwise remain forever beyond our reach. As the field continues to evolve, new theoretical possibilities emerge with each experimental breakthrough. Some physicists speculate about the existence of sterile neutrinos, hypothetical particles even more ghostly than ordinary neutrinos, which might help explain the puzzle of dark matter. Others explore the possibility that neutrinos might be connected to extra dimensions of space, curled up so small that they can only be detected through their subtle influence on particle oscillations. There are even theories that suggest neutrinos might be windows into parallel universes, quantum realms that exist alongside our own, but rarely interact with it. While such ideas remain highly speculative, they illustrate the remarkable fertility of neutrino physics as a source of new insights into the fundamental nature of reality. Perhaps most intriguingly, some researchers are investigating whether neutrinos might carry information about the quantum vacuum itself, that seething sea of virtual particles that quantum mechanics tells us fills all of empty space. If neutrinos interact with vacuum fluctuations in ways we don't yet understand, they might serve as probes of the deepest level of physical reality, the quantum foam from which space and time themselves emerge. These investigations push the boundaries of both experimental technique and theoretical imagination. They require detectors sensitive enough to measure effects that are vanishingly small, and theories sophisticated enough to make sense of phenomena that challenge our most basic assumptions about the nature of existence. Yet the potential rewards are commensurate with the challenges. Understanding the full nature of neutrinos might unlock secrets about the structure of space-time, the origin of mass, and the ultimate fate of the universe itself. As you drift deeper into the gentle currents of approaching sleep, you might imagine yourself as part of this cosmic investigation, a conscious observer embedded in the very quantum field that neutrinos probe with their ghostly presence. Your awareness, arising from neural processes that themselves depend on quantum mechanics, participates in the universe's ongoing effort to understand itself through the patient work of scientific exploration. The neutrinos streaming through your resting form carry with them not just energy and momentum, but information about the deepest structures of reality. They connect you to processes happening in the cores of distant stars, to the quantum fluctuations of empty space, to the primordial moments when the universe first began its expansion toward complexity and consciousness. In the quiet darkness of your bedroom, you are surrounded by invisible messengers from across the cosmos, particles that have traveled for millions of years to pass through this particular point in space and time where your consciousness happens to reside. They remind you that you are not separate from the universe, but intimately woven into its fabric, a temporary pattern of organized matter that has somehow achieved the capacity for wonder, for contemplation, for peaceful rest. The ghost particles will continue their eternal journey while you sleep, carrying their quantum secrets across the expanding cosmos, connecting distant realms of space and time in an endless dance of transformation and discovery. They whisper their mysteries to those patient enough to listen, to those willing to dedicate their lives to the slow, careful work of scientific revelation. And in their own subtle way, they sing you towards sleep tonight, these messengers from the quantum realm, these bearers of cosmic news who barely exist, yet somehow hold keys to the deepest mysteries of existence itself. Sleep well, fellow traveler, through the cosmic night, knowing that you are accompanied by trillions of invisible companions from the stars. And if these ghostly messengers from the quantum realm have kept you awake just a little longer than intended, well, at least you've spent that time contemplating one of the universe's most beautiful mysteries. Before we part ways on this gentle journey through the realm of ghost particles, I'd love to know once more where in the world you're listening from tonight, and what time it is in your quiet corner of the cosmos. Whether you're drifting off in Dublin as dawn approaches, settling into slumber in Singapore, or finding peace in Portland as the evening deepens, you've been part of something rather extraordinary tonight. You've followed the trail of particles so elusive they barely exist, yet so fundamental they helped shape the very universe that cradles your dreams. If this peaceful exploration of neutrino science has brought you comfort, curiosity, or simply a moment of wonder before sleep, I'd be deeply grateful if you'd consider giving this video a gentle thumbs up, or perhaps subscribing to join our community of fellow cosmic wanderers. It helps more souls find their way to these quiet scientific journeys, and it means the world to know that somewhere out there, others are finding peace in the marriage of knowledge and rest. There's something profoundly soothing about neutrinos, isn't there? These particles that ask nothing of us, that slip through our world without fanfare or disturbance, yet carry within themselves the stories of stellar birth and death, of cosmic evolution, of the very processes that made our existence possible. They remind us that the universe operates on principles both elegant and mysterious, that reality unfolds through processes more subtle and beautiful than our everyday experience might suggest. As you close your eyes and surrender to the gentle pull of sleep, remember that you are not drifting off alone. You are accompanied by messengers from across the cosmos, particles that began their journeys in the nuclear furnaces of distant suns, in the violent explosions of dying stars, in the primordial fires of creation itself. They stream through your dreams, these ghostly companions, carrying news from realms so distant that light from those sources is only just now reaching Earth for the first time. The same quantum processes that allow neutrinos to oscillate between different flavors, to exist in multiple states simultaneously, are at work in the neural networks of your brain, creating the mysterious phenomenon we call consciousness, through patterns of activity too complex for any current theory to fully explain. In a very real sense, you are part of the same quantum dance that governs these cosmic messengers, a temporary pattern of organized matter that has achieved the remarkable capacity for awareness, for wonder, for peaceful rest. Tonight, as neutrinos from ancient supernovae slip silently through your pillow, as messengers from the solar furnace dance invisibly around your dreams, as the ghostly remnants of the Big Bang itself flow past your sleeping form, rest knowing that you are part of something magnificent and mysterious. The universe is not empty space punctuated by lonely islands of matter, but a richly woven tapestry where even the most ethereal threads play vital roles in the cosmic design. The neutrino detectors scattered around our world will continue their patient vigil while you sleep, listening for whispers from the edge of existence, waiting for the next cosmic catastrophe to announce itself through a burst of ghostly particles. In underground laboratories carved from ancient stone, in chambers filled with liquid xenon colder than the depths of space, in cathedral-sized tanks of ultra-pure water, scientists maintain their contemplative watch, practicing a form of technological meditation that honors the subtle rhythms of the quantum realm. These modern temples of scientific contemplation represent something beautiful about the human spirit, our willingness to dedicate enormous resources and decades of our lives to understanding phenomena that offer no immediate practical benefit, no promise of technological advancement, no solution to pressing human problems. What they offer instead is something perhaps more precious: knowledge, understanding, a clearer picture of the universe we inhabit and our place within its vast and intricate design. The story of neutrino research is also a testament to the power of human curiosity and persistence. From Wolfgang Pauli's desperate theoretical hypothesis in 1930, proposed to save the sacred principle of energy conservation, to the underground cathedrals of today, where scientists catch ghost particles one interaction at a time, the journey has spanned nearly a century of patient work by countless researchers who believed that the universe's most elusive secrets were worth pursuing. Each breakthrough along the way has revealed new layers of cosmic complexity and beauty. The first detection of neutrinos in the 1950s proved that these theoretical phantoms were real. The solar neutrino problem of the 1960s and 70s revealed that neutrinos could transform as they traveled, oscillating between different quantum identities like cosmic shapeshifters. The discovery of neutrino mass showed that even the most ghostly particles contribute to the cosmic inventory of matter and energy. And the journey is far from over. The next generation of detectors will peer deeper into space and time, catching neutrinos from the edge of the observable universe, from the first generation of stars, from cosmic events so distant their light has not yet reached us. We may finally detect those elusive sterile neutrinos that could help explain dark matter, or discover that neutrinos carry information about extra dimensions folded into the fabric of space-time itself. Each possibility opens new questions, new avenues of exploration, new ways of seeing the cosmos. The ghost particles that once seemed like the end of the story have become the beginning of entirely new chapters in our understanding of existence. They've taught us that reality operates on scales both vast and tiny, from cosmic distances to subatomic interactions, all connected by invisible threads of quantum correlation. But perhaps the most profound lesson neutrinos offer is about our connection to the cosmos itself. Every neutrino passing through your body as you rest tonight is a reminder that you are not separate from the universe, but intimately woven into its fabric. The atoms in your body were forged in the nuclear furnaces of ancient stars through the same processes that create neutrinos. The calcium in your bones, the iron in your blood, the oxygen flowing through your lungs. All of these elements were created in stellar cores and dispersed through space by supernova explosions that flooded the cosmos with neutrino messengers carrying news of stellar death and elemental birth. In a very real sense, you are made of star stuff, and neutrinos are the invisible witnesses to your stellar heritage, the ghostly threads that connect your existence to the cosmic processes that made life possible. They've been carrying news of your origins across the universe for billions of years, silent testimony to the long chain of events that led from the Big Bang to this quiet moment of contemplation before sleep. As you drift toward rest tonight, carried along by the gentle rhythm of breathing and the soft cadence of these final words, you might imagine yourself floating in that vast sea of cosmic neutrinos, supported by invisible currents that have flowed through space since the universe began. You are not falling asleep alone, but accompanied by trillions of ghostly companions, messengers from the stars that sing you silent lullabies in a language older than worlds. The neutrino streams will continue their eternal journey while you sleep, carrying their quantum secrets across the expanding cosmos, connecting distant galaxies and distant times in an endless dance of transformation and discovery. When you wake, refreshed and renewed, they will still be there, still flowing, still carrying news from the heart of creation to anyone patient enough to listen for their whispered messages from the quantum realm. In the grand symphony of existence, neutrinos are the gentle harmonies that bind the cosmic melody together, the quiet notes that remind us the universe speaks in whispers as well as roars, in subtle influences as well as dramatic events. They teach us that the most profound truths often reveal themselves not to those who grasp and grab, but to those who wait quietly and listen carefully for the soft voices of the cosmos. Tonight, as we complete our gentle journey through the realm of ghost particles, let these invisible messengers carry you softly into dreams, knowing that you have touched, however briefly, one of the universe's most beautiful mysteries. Rest well, knowing that you are surrounded by ancient starlight-made particle, by quantum whispers from the edge of time, by the ghostly breath of the cosmos itself flowing gently through your peaceful slumber. Sweet dreams, dear listener, and may your rest be filled with the quiet wonder of a universe far stranger and more beautiful than we ever dared imagine, where even the most elusive particles play essential roles in the cosmic dance of existence.